All right. Hi, everyone. Welcome to the next CPPC seminar. So today it's a pleasure to have Jacinda here with us virtually to talk about some interesting aspects to do with the work on atomic parity violation. So I'm sure a lot of people here know Jacinda, who is senior lecturer at UQ, but she is also a graduate of UNSW, working with Victor, who's also here. And since then, she's worked, at UNSW, and then also moving to UQ, where she was also a future fellow, and is an expert on a lot of stuff to do with atomic physics and probing new physics with atoms. So thank you very much for powering through sickness and going here to give us a seminar, and I'll leave it in your hands. So thanks, Jacinda.
Thanks for the introduction, Kieran. And thank you for having me here in this seminar series. Good afternoon, everyone. Now, I really am not a big fan of online talks because it feels like I'm just talking to a black box pretty much. So I encourage you and invite you to please direct any questions that you have during the talk while it's happening, rather than saving it to the end. So please just feel free to interject at any moment. So basically this talk is going to be in two parts. So first of all, I'm going to be motivating it generally and to show you how atoms can be used to test the standard model and search for new physics. And the focus of this talk will be on atomic parity violation, but many of the key ideas and the atomic theory behind it is also related to time reversal violating electric dipole moments, which I won't go into really any detail about today. And then the second part of this talk will be on adventures. I call it adventures at the intersection of atomic and nuclear physics, an area that I've been exploring over the last few years and have been thoroughly enjoying. And this is not unrelated to what I just spoke about above. In fact, it is completely motivated by studies of atomic parity violation. And the main point here is that it turns out that understanding hyperfine structure very well and nuclear structure effects is really critically important in terms of pushing the precision of atomic theory higher. So just a schematic diagram here of an atom. We have electrons here whizzing around a central nucleus. And this is just a very just schematic diagram to show you really that an atom does contain all of the interactions within the standard model. So you have, of course, the electromagnetic interaction, the weak interaction, and the strong interactions all take place within an atom, which can make an atom essentially like a micro or nano laboratory for doing tests of the standard model and searches beyond it, as long as you come up with clever ideas of probing these. And so you would know, of course, that long distance effects in atoms are dominated mostly by electromagnetic interactions. But if we're wanting to probe the electroweak theory, what we do is instead exploit parity violating effects. So we look at those effects violating parity, and a parity operation is when you have the polar vector r going to minus r. So it's like reflection in a mirror, rotation by 180 degrees. The weak interaction is the only one of the interactions, of course, that violates parity. So we can isolate that interaction itself. And this is an interaction that, of course, is much less accessible and less studied than the others. And so it's a place where, there's room to discover new things. So this is what we do in atoms. We look and study these specific parity violating effects, thereby getting underneath the electromagnetic interactions and testing electroweak theory. And this is a shout out to my daughter who did this illustration for me to illustrate parity violation. So the lovely thing about atoms is that they're really versatile. They can be pretty much as complex or as simple as you like. There's so much variability where you can be changing the nuclear charge the isotope, the ionization degree, ripping off electrons and studying highly ionized systems. And of course, you're not limited to the ground state. You can study atoms in various states. So this means that there are many possibilities for enhancement of effects, and these effects are really tiny. So that's incredibly important. But as well, you can also look to study a system that is simple enough that it's theoretically tractable. So often there's a bit of a balance between the complexity of a system, whereby you can benefit from some enhancement, or at the same time also making it really simple enough so it can be readily studied. So just a little history on the neutral weak currents. So they were first discovered at CERN in 1973 in neutrino nucleon and anti-neutrino electron scattering experiments. And here the tracks are illustrated in the right-hand side there of those first discoveries. But the thing that many people would not know is that the first electron-nucleon interactions were seen in atomic parity violation, in atomic parity violation, I should say, an experiment with bismuth in Novosibirsk in Russia in 1978. And it was only later that the electron-nucleon neutral weak currents were seen in scattering experiments at the Stanford Linear Collider. As we know, of course, it was later still that the actual Z boson and the other weak bosons were directly produced. So atomic parity violation played an important role in confirmation of the standard model early on, and has continued to play a role since then, as I will illustrate. So just to give a little bit more of an idea of what's going on with this bismuth experiment. So due to this electron-nucleon weak interaction, due to that, optical activity is produced within the bismuth vapor. So what this means, I've just got a little movie here. So if you have shine plane, if you shine really linearly polarized light through some vapor, then you see that the plane of polarization of the light is rotated as it passes through, and it emerges then rotated from what it was in the first instance. And so what you're seeing is a coherent and macroscopic parity violating effect that happens due to a fundamental exchange of Z boson between electrons and the quarks in the nucleus. And here I'd just like to quote something from Josef Kuklovich, who is one of the founding fathers of this field and the scientific father, I could say, of Victor Flambaum and Oleg Sushkov. So this is what he said some time ago: the discovery of a new kind of a parity non-conserving weak interaction of electrons with nucleons is an example of a situation when a branch of physics, in this case atomic spectroscopy, long since believed to be classical, again proves to be at the forefront of our understanding of nature. Tabletop apparatus has proved to be an important addition to the experimental methods traditional for elementary particle physics. I'm convinced that this case is not the last, and that the time of tabletop experiments in studying fundamental properties of matter is far from over. And so with that, I'd also just like to say that, that precision tabletop experiments really has continued to have to play a big role in our understanding of particle physics, and it seems to be playing an even greater role as we're moving into the future, not only for atomic parity violation, but perhaps more so for studies like electric dipole moments. Okay, so in these studies of violations of fundamental symmetries, in order to basically do these tests, the standard model and searching for new physics, atomic structure theory is required. So here I've got on the left, I'm just showing that, measurements would do you do a measurement of a parity violating amplitude essentially, but what you want to extract from that is a value for the nuclear weak charge, which gives you the strength of basically the weak interaction from the nucleus. And in order to derive this from experiments, you need atomic structure theory. So they play a very important role here, a critical role. Similarly, for electric dipole moments, if you have a measurement of an electric dipole moment, these need to be related to the fundamental parity and time reversal violating properties at various scales. So you'll need atomic structure theory to relate it to properties at the nuclear scale, and also theory to relate it to the electron, EDM, etc. But now as well, again, not the subject of this talk, and I won't speak about it further, these sorts of studies with electric dipole moments are also moving towards measurements in molecules, where the molecular structure is playing a really important role also. So on to atomic parity violation. Any questions so far out there, by the way?
Well, perhaps you're about to explain it, but what do you mean by the parity violating amplitude? What was that E on the previous slide?
Good question. I will explain that in a moment, actually.
Okay.
So I'll continue then. Excuse me. So so the dominant parity violating effects that you have in an atom arise due to the Z boson exchange between the electrons in the atom and the quarks, of course, within the nucleus. In the case where you get the axial vector coupling to the electrons and the vector coupling to the quarks. And so you can write this as the product of these currents with some coefficient C1. And this G is the Fermi weak constant. So this coupling constant for the neutrons, you can build up a coupling constant for the neutrons and the protons as just the coherent sum of the couplings from the up and down quarks. And you can see that they're made up of, here you enter the weak mixing angle or the Weinberg angle here. So you can see that this is related directly to that particular parameter within the standard model. If you then consider this interaction and you average over all the nucleons in the nucleus, then you can form, in the end, a parity violating interaction Hamiltonian that acts on the electrons. So this then has the form where it's proportional, of course, to the Fermi weak constant. It's proportional to this nuclear weak charge that I mentioned, which is essentially the sum of these couplings coming from the neutrons and protons, and proportional to the nuclear density and to the gamma 5 matrix. Now, the reason that we can do tests of the standard model searches for new physics. Effectively, in this case, is because the standard model value for the nuclear weak charges is well defined. So just to point out generally that we can see from this Hamiltonian that if you're considering the non-relativistic limit, then the operator ends up looking like sigma dot p, which behave differently when you do a parity operation, and therefore, you can see that through that this is indeed a parity violating operator, and you would have then parity violating effects if you were to measure them. So as well as this, the amplitude, which I'm yet to still describe properly, is proportional to Z cubed, the nuclear charge. So, it's much more preferable to be studying systems, heavy atoms, where these effects are enhanced. So just to talk about what I mean by this amplitude. So because we have these tiny parity violating effects within the atom, it means that each of these states, so an S state is not a pure S state, it has a tiny admixture of opposite parity, so P half states within it. And these are admixed by the weak interaction. So this is the weak Hamiltonian, excuse me. And so this is just first order perturbation theory. And in these measurements, in the best measurement for cesium, they've measured the 6s to 7s electric dipole transition amplitude. So they drive this amplitude between these two states. Ordinarily, you can't have an electric dipole transition amplitude between same parity states, but due to the parity violating contribution, the admixture of opposite parity states, then you can proceed with an electric dipole transition. So this amplitude, EPV, is the parity violating amplitude from 6s, in this case from 6s to 7s in cesium. And this has been measured most accurately in an experiment from some decades ago by the group of Carl Wyman. And what they're really measuring is this amplitude divided by the vector transition polarizability, and this enters because they apply an electric field during their measurements, and they get some stark mixing in there in the final measurement as well. So in order to derive the nuclear weak charge from their experiment, you need a value for beta, which is supposedly well defined, but has changed recently. And as well as that, you need to have an atomic determination of this parity violating amplitude, which gives you this atomic structure factor times the parameter nuclear weak charge, which is extracted from comparison with the measurement. So this is the parity violating amplitude. So you've got 6s to 7s perturbed by the weak interaction. So in second order perturbation theory, it looks like this, with a second term with the weak interaction mixing the 7s state. And so this is the parity violating weak interaction, which is localized on the nucleus because it's proportional to the nuclear density. This is the electric dipole matrix element, and this operator pulls out the wave functions at large distances, and then you've got the energy intervals, which are sensitive to the wave functions at intermediate distances. So this means that your atomic calculations need to be really well described, incredibly well described at all distances across the full atom and not just at any one particular point. So this is a huge challenge for atomic theory. And of course, while this formula here looks rather simple, these are many electron atomic states. So for cesium, this is a 55 electron state. So evaluation of this is really at the forefront of precision atomic theory challenges. So the best calculations for these have been done some years ago by us at UNSW some 20 years ago. And then more recently, there was a calculation by a group in the States, and they had neglected to take into account some contribution, which was then added to by, again, the group at UNSW led by Victor Flamon. So just to illustrate some of the tests that you can do with atomic parity violation, well, if you take the theory together with the experiment, you extract the following value for the nuclear weak charge, which deviates from the standard model by some value with an uncertainty. And let me just go back. This here is showing a plot of the Weinberg angle as sine squared theta w, of the weak mixing angle, as a function of momentum transfer in the experiment. Atomic parity violation corresponds to the lowest momentum transfer kind of test of this Weinberg angle. And the black line shows you the prediction of the standard model. And then the various black bars show you experiments that have already happened. And the LHC result is, by the way, just shifted off there, so it's not overlaying on the SLAC result. Those experiments that are for the future are underlined here. And in red are the error bars of the projected future uncertainties for these experiments. I've also just illustrated in red here the shifted result for atomic parity violation due to a new determination of this vector polarizability. The result shifted up from an ever so slight deviation or whatever from standard model to being pretty much just on the central line. So the thing to show here is that atomic parity violation has a very special property of being highly sensitive to certain types of new physics. This includes the possibility of, there's many well-motivated theories, for introducing dark bosons that have light mass. So for instance, if you were to introduce one that had 50 MeV mass, then it could give a contribution that is illustrated by the green shaded region here, and could be picked up then in an atomic parity violation experiment in the future when the error bars are a little smaller, but would be blind to any experiments at higher momentum. So that's one of the nice illustrations here, just to show how atomic parity violation can be important really for discovering things like possible new dark bosons. And just to give you a show just more generally about the sensitivity to new physics, of course, we can be putting limits on this sort of new physics coming from new tree level physics, for example, just similar to what I showed you, a new dark Z boson, or we could have a new Z prime boson, or perhaps, it's also sensitive to radiative corrections where you could have a new fermion in a loop. But just to give you an idea of the sort of bounds that you can find from new tree level physics, you'd be probing a mass scale of lambda greater than this bunch of parameters, where kappa is the coupling constant, and then here we have the uncertainty or the deviation from the standard model value. And of course, for strongly interacting theory, kappa squared is about 1, weakly interacting kappa squared is about alpha. And if we have an uncertainty of about 0.5%, which we have for our theory uncertainty, and overall uncertainty is about that, then we have a lower bound on some new particle of about 30 kappa TeV. So we can see that we're already in the TeV scale for different sorts of models. For a Z prime boson, that gives a lower bound of about 1 tera electron volts. And at the time of the cesium experiment, this was the tightest bound, the highest lower bound compared to what was available at the colliders. So what about what sort of experiments are happening now? So there is a next generation experiment happening, or a new generation experiment happening at at Purdue University in the States with cesium. There's an experiment that's been in preparation for some time at Triumph in Canada, between collaboration of Canadian and US scientists, and then also at Tokyo. And over some years, there's also been discussions and preparatory work towards experiments with barium plus and radium plus, but I'm not sure what the status of those is at the moment. But we're hoping to get some new exciting results out of the cesium and francium experiments shortly. The thing to note is that with all of these systems, of course, we have one single electron above tightly closed shells, which means that we can study these very accurately with our theory. And also, there are some challenges with the experiment, but they're able to proceed and do accurate enough work with these systems. Excuse me. Okay, any questions wrapping up that part on parity violation, introduction and background?
Can you go back to the figure where you're showing the running of the weak mixing angle? So this value of QW, this is for cesium, right? The 73.
Yes, it is.
Okay, and I think you said, but I didn't quite catch it. What is the error budget for the nuclear weak charge for cesium? Is it all coming from the Weinberg angle, or is there some other atomic contribute? Because I would have thought because isn't the nuclear weak charge just basically the numbers of nucleons and then the weak mixing angle, or is there some other result?
I missed the actual question there. Sorry, what was?
So what the error budget? So there's minus 73. The standard model uncertainty basically, is that all coming from the weak mixing angle?
This uncertainty here.
No, so when you showed the QW standard model, there was an uncertainty on that. Is that coming from the weak mixing angle, or is there some other contribution? Yeah, this one, yeah.
Well, this is coming from probably, okay, so as well as this, there are some radiative corrections that you need to evaluate, and it comes, I guess, largely from evaluation of those.
Okay, yeah. And maybe about the specific atoms. I mean, you mentioned that there's it's easier to deal with cesium and stuff like this, but do the experiments require? Because I mean, I know cesium is like one of these clock atoms that they use. Is there also experimental reason why you can probe things more sensitively with these atoms in like group 1?
Just 1 second. I wasn't sure whether to proceed today because of this cold. No. So yeah, I would say that for cesium, experimentally, I don't know all the reasons for why experimentally it's a nice system to study, but of course the effects themselves are going to be very much enhanced in these heavier systems because you have the enhancement of Z cubed even higher than that, slightly due to relativistic effects. So that's why you want to be going as high as you can. So we're here at sort of the end of the periodic table, and with single valence electron systems so that they're theoretically tractable at the same time. So you want the heaviest single valence electron systems. I would not say that francium is an easy system to study, or even radium plus, because they're so highly radioactive.
Yeah.
And I think there's, only a couple of places where they can even produce francium, I think, and actually do such experiments. And as far as I'm aware, at Triumph earlier, they only had access to the beam for, was it 1 or 2 weeks or something a year? So they would otherwise do a whole lot of their practice in rubidium, which has, I guess, some similar kind of structure, but obviously very much lighter. So in terms of the experimental kind of things, I don't know, but yeah, you want to have, of course, a much larger effect, because the effects themselves are just so minuscule. I don't know if I mentioned that the mixing of P states to S states, and the size of this amplitude is about 10 to the minus 11. So compare that to the order of 1. So it's absolutely tiny, and you want to be trying to go to heavy systems where you can see it. And unless the theory is competitive with experiment, and the theory is the level of 0.5% compared to experiment that's 0.35, then as well you can't be extracting nuclear weak charge competitively. So we need the theory to be as good as the experimental, but hopefully even better if we can reach that. So in these new experiments, they're looking to achieve uncertainties of about about toward 0.1%. So they're really looking to do better than the current best results. They do take many, many decades to really, I guess, make significant strides with progress with these experiments, and that's why there aren't a huge number going on. But let's hope that things, that we'll have something really exciting coming up in the next years. Okay, so just moving on to the next part. So this adventures at the intersection of atomic and nuclear physics. So I'm going to be talking about hyperfine structure and the motivation for that now. So at our precision atomic theory group at UQ, one of the main goals that we have is to overall, generally, maximize the discovery potential of precision atomic experiments. And in order to do that, this basically moves through 2 different avenues. One is the development of high precision many body methods that needs to be done together with improving the benchmarking of atomic theory. So just to be clear, the thing I missed here is that what we're wanting to do is to push the state-of-the-art atomic calculations to the level of 0.1% precision, so that we can really make significant improvements to the theory, stimulate new experiments as well, so that atomic parity violation measurements are continuing. Unless the theory is improving, there's no point for experiments to continue. So the focus here, I'm not going to be talking about the actual methods themselves. I'm going to be talking about this improved benchmarking of atomic theory, and I'll explain what I mean by that. But essentially, the focus here is going to be on removing nuclear structure uncertainties that currently hinder tests of atomic theory. So now this is just showing basically how we do this benchmarking. This is a plot of the upper radial component for cesium-6s. So it's on this the scale, illustrated logarithmic scale. And what I'm illustrating basically is which sort of properties are sensitive to what parts of the wave functions. So we have, as I showed you before, the parity violating amplitude, which is made up of the sum over products of matrix elements for the weak, E1, and energy intervals. And what we want to be doing is basically testing various properties to see how good our atomic theory is across the whole scale of the atom. So weak matrix elements themselves, they're imaginary and they're not physical quantity on their own, so we can't directly test that to anything. But the hyperfine structure is something that happens at small distance scales. And so that means that if we were to compare our calculations of hyperfine structure constants with experiment, that will give us information about the wave functions and our theory at distances close to the nucleus. We can directly compare our calculations to various energies and probe the quality basically of the wave functions at intermediate distances. And then we can also calculate electric dipole transition amplitudes and compare those to experiment and probe the distances at large distance scales. So this is basically how we proceed. This is how one main route that we take to test our atomic theory. So just to be clear about this, when you're doing atomic many-body theory, it is not like doing QED or something, where when you go to higher and higher orders in perturbation theory, the next order is much smaller than the previous one. Of course, that works when you have a small expansion parameter or perturbation parameter, but in many-body theory, your perturbation parameter is the residual interaction or Coulomb interaction, so the full Coulomb interaction minus your average potential you're starting with, and that perturbation parameter is not small. So generally we use methods that sum certain terms or a series of corrections to all orders in this residual interaction. So we can't be guaranteed that when we include the next level of something, it's going to be better. So this gives us one of the best ways of testing how good our theory is, to actually just benchmark our theory against experiment for different parameters. So what we see is that energies are really good to about 0.1% against experiment. For E1 amplitudes, it's a few fractions of a percent. For hyperfine structure, what we saw is that the deviations can be quite significant, even reaching about 1%. And so that's what sort of started me down this path some time ago. And the question really was, what is it about the hyperfine structure that we don't understand? Why can't we really be modeling our atomic wave functions so accurately in that region? And the answer came back that it was sort of a little bit surprising, and it wasn't necessarily about the atomic modeling, the electronic modeling, but more about the nuclear structure that we didn't really fully understand. So that's what I'm going to be describing to you now. So just as we move into this hyperfine structure discussion, let's just start with fine and hyperfine structure. So here we've got the fine structure splitting in cesium. So we've got 6s, 6p half, 6p3 half. We get that splitting, of course, due to the coupling of the spin and orbital parts in the atom, but then due to the coupling between the angular momentum of the atoms with the angular momentum of the nucleus, we get the hyperfine structure splitting. And then we get, for example, the 6s state is going to split into these two levels defined by the total angular momentum F. And this interval is pretty famous, as I think someone alluded to before. You may know that this is a picture here of the NIST atomic clock, and this is the primary standard for the SI unit for time, the second, which will probably be superseded at some point. But right now, the hyperfine splitting in the ground state of cesium defines the second. So anyway, it's very reassuring to know that there's some very precise experimental data for us to compare our theory to. So this one, among others, that's of relevance to our studies in cesium atomic parity violation. So let's just have a little look at our modeling of the hyperfine structure. So the relativistic operator, which just shows us how the nuclear magnetic moment interacts with the magnetic field of the electrons, looks like this. And this is the Dirac matrix. In fact, I think I'm going to point all this out in a moment. Yes, that's the nuclear magnetic moment, which is proportional to the nuclear spin. This F of R describes the radial distribution of the nuclear magnetic moment across the nucleus. If you just consider a point nucleus, F of R is just 1. But if not, then it's going to be varying from 1 within the nucleus. Now, there are different ways, obviously, to model this F of R. So it's been known for many years that it's important to take into account finite nuclear size effects. So F of R should not be modeled as 1 in heavy atoms. But it was thought until recently that you could do away with just modeling it quite crudely as just so-called Bohr model or as a uniform distribution. So this is showing the density of magnetization across the nucleus to some magnetic radius. So here it's just like a uniform throughout some Bohr. Or people have been modeling this to say that, okay, let's just take the magnetization distribution to be the same as the charge distribution within the nucleus. And so this wasn't questioned for quite some time until really I started looking at this more recently. Just to say a couple of things about this. Of course, this is giving you the distribution of magnetization. So if you're looking at charge distribution, the charge distribution comes from the protons, which is given by the bulk of the nucleus. But if you're looking at the magnetization distribution, this really comes from the unpaired nucleons within the nucleus. Everything else couples up, and it's only those unpaired nucleons that have that contribute to the nucleus spin and the magnetic moment that would be giving you this magnetization contribution. And so it can be quite natural, of course, to expect that for nuclei with high angular momentum, that this distribution of magnetization can be quite a distance out from the center of the nucleus and not be something that's coming throughout the bulk of it. So let's just have a little look about how we would quantify the hyperfine constants. The hyperfine constant here is given by A. So we can describe it as a point constant, A0, and this has the finite nuclear charge contribution to it, but we're going to separate out the magnetic contribution and call that epsilon. That's known as the Bohr-Weisskopf effect. So the charge part is there. The finite magnetization contribution is here, given as a relative correction. And then we also need to take into account quantum electrodynamics, radiative corrections, because they enter at the level of a fraction of a percent, about the same level that the Bohr-Weisskopf correction enters. As well as that, this nuclear magnetic moment needs to enter as well on these sides. So we're looking at how we would parameterize this if we're to describe it theoretically. It's useful, very powerful to be describing it in this form. So that means that if you're going to compare experimental value for the hyperfine constant, which describes the level of splitting in the hyperfine structure, and compare that to a calculation in an atom that's done here, then you can only do an effective comparison of that. And because we're wanting to test our theory and go to the level of 0.1%, then we need to be able to understand these various properties to better than 0.1% in such a comparison. We need to then be able to know, I'll just say quickly, the QED corrections, the nuclear magnetic moment, the Bohr-Weisskopf effect, they all need to be understood to better than 0.1%. So in our recent studies, we went about looking into this. At the time, there wasn't even the data really for QED corrections for all the systems of interest for parity violation. And we went and evaluated rigorously QED corrections, so the self-energy and vacuum polarization corrections to the hyperfine structure. This is the hyperfine structure with the dashed line and the triangle. For these systems, and we've found that the contribution enters at about 0.5%, and it's important to take this into account when we want to be accurate to 0.1% for our hyperfine structure or within that, or to have this under control to less than 0.1%. We also have uncertainties on these, and these are all less than 0.1%. So this is under control as long as they are calculated, but they've only been calculated twice for cesium and francium, and for the first time by us for barium plus and radium plus. So that's more or less okay. For nuclear magnetic moments, these are known for those systems of interest, except for francium. They weren't known very well. The uncertainty was 1 to 2% for francium. But as it turns out, our theory is better than 1 to 2%. It's more precise. We can do our theory to about 0.5% uncertainty. So what we ended up doing is we did a study of nuclear magnetic moments for francium, and I won't go into the detail now due to time constraints. But essentially, we extracted and we determined from our theory, compared to experiment, new values for the nuclear magnetic moments with an uncertainty of 0.5%. So that was kind of a nice thing to do. It just means that they'll need to be doing an experiment on that in the future, because now we can't do our own comparisons, or now it looks like we have obviously exact agreement with experiment if we use our own values for nuclear magnetic moments. So for the other systems, though, magnetic moments are fine. For the Bohr-Weisskopf effect, this nuclear magnetization contribution, do we understand that well enough? Turns out that no, we don't. This is, if we have just a Bohr model, a uniform distribution, we describe this radial distribution. F of r would have the form of r over the magnetic radius cubed. But in the nuclear single particle model, that's relatively simple model, but sophisticated enough, you can bring in contributions from the spin and the orbital parts of the nucleons, or the unpaired nucleon. And of course, you have some contribution or dependence on the nuclear spin. So from that, you can then determine, these so-called Bohr-Weisskopf corrections in different models, in the Bohr model and the single particle model. And we also did a more sophisticated model, taking the nucleon wave function to be found in the Wood-Saxon potential and the spin-orbit interaction included. And what we saw is the following. Generally, there's quite large differences between the different models. So it's very highly sensitive to how you model these things. For francium, the difference is huge, it's 1.3%. For cesium, it's also huge. So if, we can't be testing our hyperfine structure at the level of less than 0.1% if the difference even between the model that's been used over many years, which is the Bohr one, is different from the single particle model by 0.5%. This difference is as large as we thought the theory was good to, but obviously this means that if the single particle model is the more well-motivated theory and is the correct model, then all the results that have been done over the last years for hyperfine structure should be shifted and corrected by 0.5%. So that's a huge correction. So this led us to do a number of studies into the hyperfine structure. And again, I'm just going to skip through so we've got time for questions at the end. I'll come back to that if there's questions, but we can look at what's called the differential anomaly. There's a number of really nice things that we can do to try and determine this is the question really, what is the Bohr-Weisskopf correction for these atoms? How do we probe it? How can we determine it? Particularly for cesium, which is of particular interest for us. So there's really a number of interesting properties that this Bohr-Weisskopf effect has, and I'll just go through that and then show you how we've utilized that. So the relative Bohr-Weisskopf correction, this is epsilon that I told you before. It's given by the finite, basically F and G are the upper and lower radial components of the atomic wave functions. You have the 1/r² from the hyperfine operator. It is located at short distances. That's where this comes about. This f of r minus 1, you're looking at the finite minus the point operator for the hyperfine constant or hyperfine operator. So that's where this enters. But what we want to notice is the following thing, that in the nuclear region, the electrons see the unscreened Coulomb field of the nucleus. That's where this interaction takes place, of course. Since the binding energies of the electrons is going to be much smaller than the Coulomb potential, then the wave functions with the same angular dependence are proportional. So when you're in that region, the binding energy is going to be way smaller than, say, minus z/r. Then you can neglect these binding energies epsilon in the Dirac equation. So this is the Dirac equation. We've got the potential binding energies kappa, which determines the angular momentum quantum number. I hope I'm not going too quickly for everyone. All I want you to see is that if you neglect epsilon, the binding energies, which is the thing that depends on principal quantum number, if that can be ignored, then there's no dependence on principal quantum number, and every wave function, say a 6s, 7s, 8s, 9s electron, is even 1s electron is going to be proportional. The wave functions will be proportional because there's no dependence anymore on principal quantum number. So this means the Bohr-Weisskopf correction for 6s, say, is going to be equal to the Bohr-Weisskopf correction for 8s for cesium. It's just something to note. Another thing, in the nuclear region, if you have a heavy system, then this potential minus z/r effectively, but of course it's going to be distributed, is going to be much larger than mc². So that's this term. That means then we have in this equation V of r, we neglect epsilon, this is V of r, we neglect epsilon and 2c². And you see then that there's a symmetry in this Dirac equation for the upper and lower radial components, that if you change k to minus k, then you have the symmetry across here. If you change the sign of kappa and an F to a G, then you'll see that, I feel like this has gotten a little bit technical, that the upper radial component for an S state is proportional to the lower component for a p-half state, etc. Essentially, what this means, when you all bring it back to this Bohr-Weisskopf effect, is that any Bohr-Weisskopf effect in an atom can then be related to the Bohr-Weisskopf matrix element for a 1s state of a hydrogen-like ion. Okay, that's the crux of this story. So generally, people had thought that you need to evaluate this in some rather sophisticated way and understand the, have a nuclear model and do these calculations. But in fact, everything can just come back to the 1s state of a hydrogen-like ion. So if you can do that, then there's lots of sort of nice things that you're able to take advantage of. By the way, how much time do I have? I'm just wondering.
We usually go until the hour with questions, so 5 minutes, 10 minutes.
Okay, that sounds good. So I won't skip this then. Okay, so the first thing that we proposed was to do the following. This was really nice. Because we noticed, of course, that this Bohr-Weisskopf effect is going to be the same for different states with the same angular momentum, so for different S states. What we can actually do is take the ratio, it's not all clear from this equation, but we can take the ratio of an experimental hyperfine structure constant divided by the ratio of divided by the hyperfine constant from some calculation for that high state. So you can take this with no input for the nuclear magnetic structure whatsoever. So you just calculate it for a point nucleus. And then this is actually, you can then insert that instead of putting in the nuclear structure parameters from the beginning. So usually you need to assume a nuclear model and calculate it and so on. But in fact, you can replace that from this ratio of experiment to theory for high states. And then you can go and do your atomic calculation for a lower state, and then that's your total theory value. So that's your theory input, a theory input for high states. Nothing put in by hand at all for nuclear structure. It all comes out of this ratio from experiment to theory, and it's the real nuclear structure. So that's really nice. We proposed that this be done in order to get around the fact that we don't know the nuclear structure, and this is producing a lot of problems. So that ended up stimulating a number of new experiments by the Purdue group, and they did measurements for the high states for 12s, 13s, 8 and 8p half for cesium. And there's a couple of things to note. So with this equation, actually, with this ratio, you can do two different things. If the theory uncertainties are not correlated for your calculations of the ground state and the higher state, then this works as, replacing the Bohr-Weisskopf effect with this, essentially. But if the theory is correlated, then in fact the uncertainties cancel, even if they're not very correlated, the uncertainties cancel, and you can do ridiculously high precision predictions of hyperfine constants. So that's what we did. So this is our predictions from 2019, where we made predictions with unprecedented accuracy or precision for 12s and 13s. So at the time, the best experiment had an uncertainty that was 5 to 10 times larger uncertainty, and there's no uncertainty for the previous theory. And then this latest experiment that was just published last year confirmed our result. And here we've calculated this with an uncertainty of about 0.05%, so well within 0.1% from our predictions, confirmed by these latest experiments. And then this year, they published their results for p-half. So our result from the ratio method, we predicted 42.93. At the time, the previous experiments had much larger uncertainties. Previous theory had very different values altogether. And then our value was confirmed by experiment. So that was really very exciting. Okay, so two other things, and then we can wrap up. So, okay, so this idea that in fact you don't need to have any input from nuclear structure, because even if you do sophisticated nuclear structure, the Bohr-Weisskopf effect uncertainty is actually so large that it's still not of interest to us and doesn't help us in this comparison. But let's say we want to obtain this correction. We could obtain it from directly from a hydrogen-like experiment where they have done such things before. So if you do an experiment for a hydrogen-like system in the state 1s, then of course they have a point-like contribution, a Bohr-Weisskopf correction, and then the QED correction. This can be calculated with very high precision. This can be measured with high precision. And then this can be calculated also with high precision. Then you extract this Bohr-Weisskopf effect. And so that's been extracted with an uncertainty on the order of 1% for thallium, lead, and bismuth before. So that's amazing. And so our proposal was, okay, just take the result from this experiment and then throw it into the atomic theory, basically, with some screening factor. So here's your atomic hyperfine constant, point like QED, etc. And this thing, which has the largest uncertainty usually from first principles, because we can't measure this, instead, this should be deduced from a hydrogen-like experiment, and then we can calculate the screening factor really accurately. So that's what we propose, that in fact, these problems are separable and that this screening parameter is independent of the nuclear model. We can calculate it really precisely for many of the states. And actually for S states, it's almost 1 anyway. So that's what we've proposed. And now that's the subject of a proposal that's being written up at Max Planck Institute for Nuclear Physics in Heidelberg, where they're hoping to do experiments with hydrogen-like cesium to extract that for use for us. Okay, and then the most exciting thing that has happened more recently is that in fact, there turned out to be some historical data on muonic hyperfine structure for cesium. So let's just talk about what that is. So we have a cesium atom, and then they inject a muon, which then of course orbits around the nucleus. It's pretty much sitting on the nucleus because it has a mass that is 200 times heavier than the electron. So it's really sampling the nucleus really well. And there is old data from the, I believe, 60s, for that hyperfine data in the 1s state of muonic cesium, and you can then just extract the Bohr-Weisskopf effect empirically for that system. So what we proposed and implemented was to extract the Bohr-Weisskopf effect in muonic cesium and then translate it to a Bohr-Weisskopf effect in atomic cesium. And so we do that in 2 stages. First, we translate it from muonic cesium, translate it to hydrogen-like cesium, and then using this method we proposed here to translate the hydrogen-like case to the many electron case. So this is just reminding you of some of the Bohr-Weisskopf effects for the cesium atom. Single particle model, it's minus 0.2%. The Bohr model, it's minus 0.7%. Remember, there was 0.5% difference between. And this is showing just the results at different stages for the empirically deduced Bohr-Weisskopf effect from muonic atoms to neutral atoms. So we were able to test our procedure because there is experimental data not only for muonic thallium and bismuth, but also hydrogen-like data for thallium and bismuth, as I mentioned. So let's just have a look at what we did, and I'll explain you. So we extract the Bohr-Weisskopf effect for the muonic system. We did QED calculations and atomic calculations, basically for the muon, treating this almost like a heavy hydrogen-like system. We could extract then this Bohr-Weisskopf effect. Once we evaluated QED, we evaluated this one. We have experiment for this term for the muonic case. And this is the result. So for muonic systems, the Bohr-Weisskopf effect is huge. It's, on the order of 50% or 100%. It's massive. It gives most of the contribution or a lot of the contribution to the hyperfine structure. And then we translated this to the hydrogen-like ions. When we do this from the muonic experiment, these are the results for thallium and bismuth. And then we can compare directly to the experiments in hydrogen-like thallium and bismuth and compare the results, and we see the results are pretty much in agreement. And so then we know that our procedure works, and then we proceeded to do the same thing for cesium. We translated that to a hydrogen-like cesium atom, and and then we were able to translate to a many electron cesium atom. So the result is then 0.24 or minus 0.24, which then verifies basically the single particle model, though with some relatively large uncertainty, but definitely rules out the Ball or Fermi model that's been used over the last 30 or so years beforehand. So it's telling us that we really have been modeling the Ball-Weisskopf correction incorrectly, and now we have some idea how to do that, and some also more exciting ideas how to proceed further. So finally, summary on the Ball-Weisskopf effect. Accurate modeling of the finite magnetization distribution is important for hyperfine comparisons. Through that, it means we can test the atomic wave functions in the nuclear region, and only then, once we can test them, can we actually then continue to develop the theory. So we've got something to benchmark it against and know that we're actually improving. So this will help us to reduce the atomic parity violation theory uncertainty to 0.1%, which is our goal within the next years. It's also really important, this Ball-Weisskopf effect, for testing nuclear structure theory, for determination of nuclear magnetic moments, for probing the neutron distribution within atomic nuclei, which is otherwise an incredibly difficult thing to do, and also gives a test and can be used for tests of quantum electrodynamics. So finally, I just want to wrap up overall and hope that that you see as well that atoms can be used, of course, to do breakthrough particle physics, and there's lots of exciting stuff going on. I focused on atomic parity violation. That in going forward, we've needed to do some work at the intersection of atomic and nuclear theory. But this has been kind of exciting, and there are a number of interdisciplinary discoveries that can come out of that. And now we've been able to make some nuclear physics insights, which will feed back into our atomic precision theory and development and advancement of atomic parity violation. And finally, precision atomic theory is a necessary and difficult part of the problem, and we're proceeding with that to reduce atomic theory uncertainties. And finally, thank you everybody, and a thank you to my group and collaborators. These are the people that have been working on the hyperfine structure related work and Ball-Weisskopf effect. And we have a PhD stipend available in our group to work on this project in the future, and also a postdoc position that is open that is yet to be advertised. Thank you.
Thank you very much. Yeah, thank you very much for that very stimulating talk. Let's have some questions. Anyone want to go first? Bruce?
Jacinda, for clarification, when you were speaking earlier about the approximations made in the nuclear calculations, this form factor for the magnetic moments, in addition to the Ball model, you listed single particle. Is that really naive single particle, like I teach introductory students, or does it include core polarization and other such?
Yeah, good question. So first of all, just to be totally strict, so that looks like a form factor, but is not strictly a form factor, but it's definitely related to one.
Yep. Good.
And
fine.
Next, yes, so these models are, one of them is a very simple model. The other one is a little bit more sophisticated, just because we use Wood-Saxon potential in order to model the nuclear wave function, etc. But these are still straightforward, but they're straightforward enough that you can integrate them very easily into your atomic code. So you're bringing in a more sophisticated nuclear structure model into atomic physics modeling. But we're actually working, we're working with Professor Kowalska at CERN, who's doing experimental work on all this stuff, but also with Jacek Drobachevsky, who's in York at the moment, and he's an expert in microscopic nuclear theory. And indeed, in that project, we're working towards doing detailed microscopic calculations of Ball-Weisskopf effect. But it's really an area that has not been explored very much at all. And so it's still in its kind of early stages. There are definitely a number of older calculations of this, but it hasn't been revisited in the last decades, actually. And so there at the moment is not really much work going on in terms of the microscopic stuff. But
so is it calculational difficulty that's the reason for, I mean, I accept your statement that what you're introducing in this is the current absolute state of the art. But in terms of applying what's already known about nuclear structure, it seems there must be some non-trivial reason for in 2023 or 22, you're introducing seriously for the first time non-trivial structure effects that are known since 70 years. Is it just because the calculations have been too hard up to now, or is it neglect? Is it sociology? Is it what?
Okay, so I mean, I guess there's two things. I mean, one thing is, I suppose, because it's right at the cross section of two different disciplines, and either you simplify the atomic theory and do the more sophisticated nuclear theory, or you go the other way around and do the simple nuclear theory and the more sophisticated atomic theory. And there hasn't been very much that integrates the two of them at an advanced level. I would say that there's maybe been some level of maybe neglect or lack of interest in that area. I think that but this is all picking up again. So definitely there was work that was done. I mean, Bohr and Weisskopf did their stuff. They introduced this in the 50s, I think it was 1950, you know, and then after that, there was quite a lot of work done in this area, and then it was pretty much dropped. I guess people went in their different ways, and only more recently are people really coming back, similar to, I think, muonic kind of areas. So now there's, you know, some work going on in muonic atoms, but I don't think there were very many studies for many, many years, even though the studies earlier on were really important in establishing things like charge radii and so on in muonic atom experiments. But now, you know, now there's been a sort of, I don't know, more interest coming into that, and at Peter Scherer Institute, they now, and elsewhere, they have now programs looking at doing a whole lot of new experiments with this. So I think it's just some area that really people had looked away from, and now there's more interest in that now. There's definitely been a lot of work on nuclear moments, but not actually to do with this detail of the distribution and the magnetic structure. But it is really nice as well, because there's more of a push, of course, trying to understand what the neutron distribution is in nuclei, and this is a way to actually to grab onto the neutron distribution, because then you can study a series of isotopes where the unpaired nucleon, or you're adding, you know, a neutron each time, and then you're able to see what the magnetic contribution is coming from the addition of that neutron, and so you can kind of map out at least the outermost parts of that neutron structure. So this is sort of, it's getting more and more interest at the moment, that, yeah, maybe there's just been some lack of, I don't know, some oversight perhaps in the last years.
Thank you.
Anyone else? Please go ahead. Maybe I'll continue then. So picking up on the idea of you know, using this to probe new physics and, you know, new particles, perhaps you use the example of the Z prime. Is are there any other, you know, specific ideas or particles that you think are potentially on the horizon? Like, say, if you were to, you know, achieve your goal of reducing the certainty below 0.5%, you know, let's say somehow you were able to get to 0.1%, 0.01%, and then experiments could match it. Is there some sort of holy grail type of new physics scenario which people are kind of looking to probe in as this sort of, all of this stuff gets better?
Well, I guess one thing that I mentioned there were the dark bosons, for instance. So that's something that, you know, atomic physics could be particularly sensitive to, and hasn't been ruled out yet, as far as I'm aware. Z primes, I don't know, anything that sort of would give a parity violating effect in some system, it would be sensitive to. But as well as that, yeah, I mean, they're also, these are just the direct new physics. There's also the radiative corrections, where you can have some new fermions, say, within the Z loop. And I'm not, sorry, the Z exchange. And there, I didn't show that, but, you know, depending on how you express, I guess, the results, you're quite sensitive to a very different sort of parameter space. So when you look at that for the radiative corrections, you know, you see that atomic parity violation gives you sort of orthogonal constraints than what you get from other scattering experiments. So it's not simply just a matter, I guess, of looking at that particle, but also looking at, you can also constrain other sorts of parameters, not just the masses of things, and in a more kind of sophisticated way.
I'd also like to just understand a bit more broadly when you're talking about these theoretical uncertainties. In what sense should I interpret them? Are these sort of estimates based on like the size of the next term that you haven't included in the calculation, or is there sort of a statistical meaning to them, like you propagated uncertainty on some other parameter into the uncertainty on that calculation? Like in a general sense, can you describe what the uncertainty on the theoretical uncertainty kind of means?
Okay, so theoretical uncertainty on atomic parity violation theory, you mean?
Yeah, you're specifically theory on. Yeah, I mean, I'm talking more broadly about like the whole talk. When you quote theoretical uncertainty on things, like what is the sort of meaning of that? Yeah.
Yeah. Okay. So there are different ways of doing this. There's two main, I suppose, approaches. One is to do exactly that. I mean, yeah, there are two main approaches. One is to basically understand what you're missing. For example, higher order contributions of higher order correlation corrections, any missed QED effects, any other sort of missed effects, contributions of nuclear structure uncertainty you don't know about, blah, blah, blah. All these things that directly go into your calculation of the atomic parity violating amplitude. Also numerical uncertainties, the method, all of these. So there's that one way of doing it that way, which is what we do. And then there's the other way of really just saying, okay, here's our amplitude. We know that we need to be reproducing. If this amplitude is accurate to this level, it means we should be able to accurately describe, calculate the properties, these properties this well. And so you do a statistical analysis of the uncertainties for a number of different hyperfine constants, for energy intervals, and for E1 amplitudes, and then you survey that and then put an uncertainty on that based on that. And so we look at the two approaches, we do those very carefully, and then bring those together and make the uncertainty usually larger than what it might otherwise be. So we're usually quite conservative with our uncertainty.
Victor, you got your hand up.
Yeah, I have something to add because we have questions which I may clarify. There was we published a paper in Physical Letters which gave the best limits on extra Z boson of low mass, basically for arbitrary mass up to 100 MeV. So it's the best limit on the extra Z boson, but of low mass extra Z boson, not for high mass extra Z boson. So it's available. So atomic physics already works for kind of study of new physics. Then there was a question about uncertainties of weak charge or some nuclear structure uncertainties. There is some uncertainty related to kind of radius of neutron distribution, because neutrons give dominating contribution to weak charge. It's under control because it was investigated theoretically, experimentally, and this error is pretty small. So nuclear uncertainties at a weak charge contribution is pretty small. Then we found that actually problems is not reduced to weak charge. There is a long-range parity violating interaction. So because mass of Z boson is big, it's practically contact interaction because Compton wavelength of Z boson is much field is much smaller than nuclear radius. It's a contact interaction. We found contributions which is relatively long range. Radius is electron Compton wavelength, for example. Or there is contribution even related to neutron mass, which is much bigger. So this long range contribution is also under control. But one should take it into account. So in addition to weak charge contribution, purely within standard model, there is a long range contribution, which is not, strictly speaking, reduced to weak charge. So this work continues and probably never end. But many body theory is a major concern, which it was explained pretty well, so I have no comments about this. So that's it. One more thing I forgot to tell. There is a method which completely, practically completely exclude atomic calculation uncertainty. It's isotopic chain method. When you measure ratio of parity violating effects on different isotopes. It was realized in Woodker group in mines. It was proposed by us long time ago. It was a few years ago realized by Woodker group, and we also measured, roughly speaking, ratio of proton to neutron weak charge. Because cesium experiment is sum of proton and neutron weak charges, and you calculate ratio of parity violating effects. Roughly speaking, it's ratio of proton to neutron weak charges. So it's another approach which excludes uncertainty of atomic theory, but it put more pressure on experiment, because to measure ratio of parity violating effects on different isotopes, you need much higher accuracy, because this ratio is smaller than total effect. So, for example, when it was measured in ytterbium, the maximum difference of nuclear weak charges is it's 10%. So you need much higher experimental accuracy, but still this method produces competing results, and it excludes atomic uncertainty.
So it's sensitive to quite different new physics.
Yeah, yes, but it also gives limits on extra Z boson of low mass. It was published in this paper. I happen to be a co-author for this experimental paper, so I know pretty well what is what. Okay, thank you.
Yeah, thanks, Victor. So yeah, well, gone over a bit.